Hang tough. Never, ever give up, regardless of the adversity. If you are a leader, a fellow who other fellows look to, you have to keep going. Dick Winters. Love this guy. If you guys have read Band of Brothers or watched the miniseries, is a great leader. All right, let's move on. So here's the battle plan. Unfortunately, last night's video discussion did not record correctly, so I'm having to re-record this today. So it's not going to be exactly like we did yesterday. We'll cover emergency procedures. We're going to bypass this week's questions since there's nobody here. We'll get into steep turns and ground reversal maneuvers and Q&A. Of course, if you have questions, just drop them in the comments and I'll address them as they go. All right, so last night we talked about the different systems. We have the pedostatic system, which includes our airspeed indicator, altimeter, and vertical speed indicator. The gyroscopic system, which is driven by the engine, by the engine-driven vacuum system, which covers the attitude indicator and the heading indicator, and the electrically driven gyroscope, which is the turn coordinator. Now, let's say, for example, we have our pitot tube and it gets blocked with ice or some bug gets in there. What's going to happen to our instruments? Well, the pedostatic system, or the pitot tube, provides ram pressure for the airspeed indicator. So if you have something blocking your intake, it's basically going to get no ram air, and so your airspeed indicator is going to go to zero. Now, what happens if you have ice and it covers the drain hole as well? Well, you're going to get a bunch of high-pressure air trapped inside there, and it's going to basically stay at whatever airspeed that you have, unless you change your altitude. If you climb up to a lower density of air, the air pressure in here in your pitot tube is going to be greater than what you'd expect. So it's going to be like, wow, you must be going really fast to have this great pressure in here compared to the static air around the aircraft. So it's going to indicate a climb. Now, if you descend to higher pressure air and you still have this air trapped inside your pitot tube, it's going to be like, wow, you're not really going all that fast compared, or your the pressure inside the pitot tube isn't as high as the static air around. So you're going to indicate a decrease in airspeed. So in short version, if your pitot tube is blocked both the front and the back, then as you climb, your airspeed indicator will indicate an increase in airspeed. If you descend, your airspeed indicator will indicate a decrease of airspeed. Yeah. Of course, if you have questions, just drop them in the comments. Let's move on to steep turns. A steep turn is a maneuver that consists of a constant altitude turn in either direction using a bank angle between 45 degrees to 60 degrees. For private pilot, we're going to be at 45 degrees, 50 degrees for commercial pilots. The steep turn will cause an overbanking tendency, which we're going to talk about, during which maximum turning performance is attained and relatively high load factors are imposed. We'll talk about what that means here in a bit. Why do we care? We want to develop smoothness, coordination, orientation, division of attention, and control techniques necessary for the maximum performance turns. The pilot understands the effects of the overbanking tendency and how to counter it. We're going to cover the maximum performance turn, the science behind turns, and how to fly a steep turn. Now, as we enter a steep turn, we're going to be thinking about a couple of things, right? So first of all, if we want a really, really tight turn, we're going to want a fast rate of turn and a small radius, right? And so if we are going really, really fast, it's going to take us longer to complete a circle than if we're going relatively slower. We can complete the circle faster if we are going at a slower airspeed. We can also change the angle of bank that we fly the turn at. If we're flying a very shallow angle of bank, it's going to take us longer to complete the turn than if we were to fly a very steep angle of bank, right? So your rate of turn and your radius will be a product of your airspeed and your bank angle. So a higher airspeed is going to be a bigger radius. A higher bank angle is going to be a smaller radius. Now, your maximum bank angle is determined by the load factor, which can be maintained without stalling or exceeding structural limitations. Remember that your load factor is the weight of the aircraft plus the centrifugal force. We refer to it as G's. How many G's can your aircraft sustain? Check your pilot operating handbook. Typically, 50 to 60 degrees of bank is your max. So, but yeah, check your POH. Let's talk about the science behind turns. When we're flying straight and level, we have the vertical component of lift. Our lift is basically completely vertical, right? It's counteracting your weight, and so you're nice and balanced. Now, when we roll into a turn, now our lift vector gets changed from purely vertical to vertical and horizontal components. And this horizontal component of lift is what turns our aircraft, right? But now that we are changing our lift vector, we don't have as much vertical lift as we did when we first started the turn, or when we were straight and level. So we need to compensate for that lost vertical lift, or we are going to descend. This additional lift is the lift required to maintain our altitude. Now let's talk about load factor and our stall speed. Assuming level flight, as the bank increases, your load factor and stall speed are also going to increase. So if we are straight and level, we're pulling 1 G. If we go to a 60-degree turn, we're going to be pulling 2 Gs. And our stall speed is going to increase by about, 40% almost? So as we increase the bank angle over here, our load factor is going to go up exponentially. And so is our stall speed. So the steeper your turn, the faster you're going to be when you stall. So be aware of that. So here you had 60 degrees, 2 Gs, 70 degrees, 3 Gs. So keep in mind, as you roll into a steeper turn, you're going to increase your load factor. So you and your passenger are going to feel greater Gs, and you're going to feel pulled into your seat. And you're also going to increase your stall speed. Now let's talk about adverse yaw. And we've mentioned this before, but I love talking about it. So as we are flying straight and level and we want to execute a turn, we're going to raise one aileron and lower another aileron. Now the lowered aileron they're both going to change the camber of the wing. And one wing is actually going to generate more lift than the other wing. The other wing is going to generate less lift. And as you have this differential of lift, or this wing is going to roll up and this one's going to descend because this wing is generating more lift, right? Now remember, a product of lift is drag. So the wing generating more lift is also going to generate more drag. And let's assume this is moving backwards, not down. And this wing is going to generate less drag. And now you see, we're trying to roll to the left, but now our wing is getting dragged, and so we're actually going to yaw. Our nose is going to get dragged to the right. This is called adverse yaw. How do we account for it? We're going to add in a bit of rudder, coordinated rudder, to account for that adverse yaw. Now there's also something called the torque effect. Let's actually zoom out a little bit and talk about helicopters for just a second. If you have a poorly drawn helicopter here, you've got the rotor, right, and it turns in one direction. Well, Newton's laws of motion say that for every action there is an equal and opposite reaction. And so the body of the aircraft, the fuselage, wants to turn in the opposite direction of that rotor. And so how do we account for that? We add in another rotor here at the back, the tail rotor. And this tail rotor keeps the helicopter from spinning in the opposite direction of the rotor blades. Now the Cessna, or any propeller aircraft, also has that tendency. There's a fast-moving propeller that is spinning in one direction, and the aircraft wants to roll in the opposite direction of that spinning propeller. That's that torque effect. Now, when we go into a left turn, this actually encourages that torque effect, encourages our left turn, and can result in a skid. So remember, use your rudder pedals to coordinate the turn. In a right turn, that left turning tendency of the aircraft is going to discourage our right turn, which can result in a slip. And again, in both cases, the answer is use your rudder correctly. Now let's talk about the overbanking tendency of the aircraft. Now, in a relatively shallow bank, it's not very pronounced. But in a very steep bank, when you are executing a very high rate of turn, your inner wing is going to move slower compared to your outer wing. Because they're trying to stay level, the outer wing is actually going to move faster in the circle than the lower wing. It has a greater distance to travel. And now because it's moving faster, it's going to have a higher airspeed. And of course, that higher airspeed is going to generate more lift. And so this wing is going to want to keep banking in the direction that we're turning. And so at some point, we're going to have to put in opposite control pressures to account for this overbanking tendency, right? So, just realize that the outside wing travels a longer path relative to the inside. The higher airspeed results in the outside wing generating more lift, and more lift equals more bank. And so we need to put in opposite aileron pressure. Yeah, so like we said before, in a shallow bank, you're probably not going to notice it. This difference is going to be overcome by our lateral stability. But the steeper our bank gets, the more likely it is to notice this overbanking tendency. And just remember, opposite aileron pressure may be required to maintain the proper bank angle. Now let's talk about actually performing the maneuver. Now, every time we go perform a maneuver, whether in the real world or on a check ride, what's the first thing we do? Clearing turns. That's right. We're going to tell the DPE, sir, I'm going to clear the area before we proceed. So we're going to lift up our wing, look to our left, and execute a nice gentle turn to the left, clear the airspace, and then make another turn to the right, and then go back to our heading. Right. Now we're going to select an outside reference like a mountain or a building, and then use our heading indicator bug and say, this is where I'm starting my maneuver, on this heading with my nose pointed at that mountain over there. We're going to select an altitude that is appropriate. For this isn't a ground reference maneuver, so it's good to have more altitude rather than less altitude. So, pick an altitude that is going to give you plenty of time to recover if something goes wrong. So we've got your altitude selected, our heading bug, our outside reference. We've done our clearing turns. Now we're going to roll into the maneuver. We're going to put in, nice, crisp aileron pressure, coordinated rudder pressure, and we're going to enter that bank. Now, what's something that's going to happen? And we've talked about this earlier. We're going to lose a lot of our vertical lift. So as we turn, roll left, add a bit of rudder, and then you're going to use your trim tab, 1, 2, 3, towards the aft position to account for that extra lift that you need. So roll into the turn, add some rudder, and then 1, 2, 3 on the trim tab. And then what you're going to do, if this is your horizon, you're going to keep your angle constant and drag your nose across the horizon. Keeping your nose on the horizon is going to be the best way to maintain your altitude. Now, as always, we're going to keep 90% of our attention outside of the aircraft, clearing the airspace, looking for other traffic, looking at, oh, that's a terribly drawn airplane, looking for mountains or terrain, and we're just going to keep our nose on the horizon as we drag it across. And yeah, like I said, 90-10 rule, 90% of your time is spent outside looking for traffic or terrain or maintaining this constant bank angle. And if you notice that you are losing altitude, a lot of people will try to just pull up on the yoke or on the stick to try to fix that. But because we are in a very steep bank, that's when we're going to notice that overbanking tendency. The aircraft's going to want to keep rolling. What you actually want to do is add in opposite aileron pressure, roll out of the bank just a little bit. It allows you, plus or minus 5 degrees of bank. So roll out of it just a little bit and then add some back pressure. And that's going to help you maintain your altitude. Keep your pitch adjustments nice and smooth. And I like to look at my vertical speed indicator. If you can nail that at 0 feet per minute, you're going to maintain your altitude the entire time. So drag your nose across the horizon, and then when we are half of the bank angle away from our heading, for example, if we're trying to get to a heading of 270, when our nose is at heading 330 in a 60-degree bank turn, that's a degree, that divided by 2, that's going to be 30 degrees. So we're going to lead off our turn or our level off by 30 degrees if we're in a 60-degree bank turn. So 30 degrees before we get to 270 is 300. We're going to start our rollout 30 degrees ahead of our heading, and that should put us in line to level off right at our assigned heading or our selected heading. Now, remember that we put in a lot of aft trim to start this maneuver. So when you roll wings level, what's something that's going to happen? You suddenly have way more lift than you need, and you're going to accidentally climb up. So when you roll wings level, use your trim tab, roll that trim tab back to where you had it before, roll it forward 1, 2, 3, and then you should be back at your pitch, power, and trim setting that you were at before you started the maneuver. And then establish straight and level sight. Sight picture, here's your cowling, or here's your dash with your instruments, and you should be back to, you know, a good VFR sight picture. And again, 90-10 rule. Questions? Of course, I'm re-recording this, so if you have questions, just drop them in the comments.